A dead rocket is falling toward the moon, and on August 5th, its long, silent journey is expected to end in violence. It has no crew, no guidance, and no mission left, yet astronomers across Earth are preparing to watch it. For more than a year, this 12-meter machine has wandered through the invisible frontier between Earth and the moon. Now calculations place it on a collision course with the lunar surface, near a crater called Einstein.
But the greatest mystery is not whether it will hit. It is what, if anything, we will actually see.
This is the story of a forgotten Falcon 9 upper stage and an accidental impact that could become a unique scientific experiment.
The predicted moment is August 5, 2026, at approximately 6:35 Coordinated Universal Time.
The expected impact point lies on sunlit terrain near the moon's eastern limb, close to Einstein Crater. It is expected to strike at 2.43 kilometers per second, approximately 8,700 kilometers per hour. Researchers estimate that the empty stage may still have a mass of approximately 4,000 kilograms. Together, that mass and speed would deliver nearly 12 gigajoules of energy, comparable to roughly 3 tons of TNT.
The object is approximately 12 meters long, making this far more than a tiny fragment of ordinary space debris.
Yet the collision will not resemble a Hollywood explosion. The moon has no atmosphere to support a billowing ball of fire. The first observable signal could be a flash lasting less than a single second. Afterward, an ejecta plume could lift above the surface and remain detectable for several minutes.
When the dust settles, scientists expect a new crater approximately 20 to 30 meters across.
To understand how an ordinary rocket became a lunar projectile, we must return to the beginning of its journey.
In January 2025, a Falcon 9 launched from Earth, carrying 2 privately built lunar landers.
They were Firefly Aerospace's Blue Ghost 1 and iSpace's Resilience lander, each beginning a separate mission to the moon. The rocket's upper stage performed its job, sending the 2 spacecraft onto the paths required for their lunar journeys. But after separation, the empty stage was abandoned in a high Earth orbit that repeatedly crossed the moon's path. This region is neither ordinary Earth orbit nor stable lunar orbit. It is a complicated gravitational borderland. With no active guidance, the stage could no longer correct its path or choose where its journey would end. Its motion was shaped by Earth, the moon, the sun, and even the gentle pressure of sunlight. Objects this distant can be extremely difficult to track, especially when their brightness and orientation constantly change. Each new observation slightly improved the orbit, allowing astronomers to project the object's future path more accurately. Orbit specialist Bill Gray connected the observations and identified the approaching collision during 2026.
As more measurements arrived, a wide cloud of possibilities narrowed into a predicted impact location and time.
Unlike Earth, the moon has no substantial atmosphere to burn the stage, slow it down, or soften its arrival.
Nothing now stands between the falling machine and the ancient surface below it.
The predicted site is near Einstein Crater, at approximately 88 degrees west and 15 degrees north.
From Earth, that location appears close to the lunar limb, the curved boundary between the moon and space.
A subtle rocking motion called lunar libration brings the predicted impact site just inside our view. At the predicted moment, the moon will be near last quarter and approximately 56% illuminated.
That position creates both a serious obstacle and one possible advantage for observers. The best darkness is expected across South America and low to middle latitudes of North America. Observers in Europe and Africa face daylight, although specialized infrared equipment may still offer a possibility. The moon must also be above the horizon, and a low viewing angle can make Earth's atmosphere disturb the image. This is not expected to be a naked-eye event, and binoculars are unlikely to reveal the moment.
A telescope and a sensitive high-speed camera provide the most realistic chance of recording anything useful.
Researchers recommend recording at 20 frames per second or faster, because the flash may vanish between ordinary exposures.
The greatest problem is that the predicted impact point is already illuminated by the sun.
Lunar impact flashes are normally recorded against darkness, where even a brief spark can stand out clearly. Since 1999, telescopes have recorded hundreds of natural impact flashes on the moon's unlit surface. Natural meteoroids are usually far smaller than this stage, but they travel many times faster. Paradoxically, the larger rocket could create a dimmer flash, because impact brightness depends strongly on velocity. A collision with loose lunar regolith could produce a stronger shock and a brighter visible signal. But if it strikes exposed bedrock, the flash might be too faint for even powerful telescopes to detect. Published estimates range from approximately magnitude +3 to fainter than +15, an enormous uncertainty.
That means the cameras could capture a remarkable signal, or appear to capture absolutely nothing.
Astronomers are therefore searching for 3 separate clues: the flash, the plume, and the crater left behind.
The flash would be produced as part of the stage, and lunar material are heated and vaporized.
The plume may be easier to detect once its highest particles rise beyond the bright lunar limb.
Without air resistance, every fragment will follow a clean ballistic arc controlled almost entirely by lunar gravity.
The stage's hollow structure, uncertain orientation, and impact angle could make the collision unusually complicated.
Because the stage should arrive at an angle, the ejecta may spread unevenly across the surrounding terrain.
Computer simulations suggest the collision could excavate more than 1 million kilograms of lunar material. The smallest and fastest particles may climb several kilometers above the surface, potentially making the plume visible from Earth. While heavier fragments would return quickly, fine debris could remain above the moon for minutes, perhaps longer. Models indicate that some debris could travel hundreds of kilometers before falling back onto the surface.
Scaling calculations predict a crater roughly 27 meters wide and approximately 5 meters deep.
That crater will be much too small for telescopes on Earth to resolve directly.
NASA's Lunar Reconnaissance Orbiter is expected to compare images taken before and after the collision.
Korea's Pathfinder lunar orbiter is predicted to pass within kilometers of the stage approximately 2 minutes before impact.
Across Earth, professional observatories are preparing different instruments to search for different pieces of evidence.
At Apache Point, a 3.5-meter telescope is scheduled to perform rapid imaging of the impact region. The Lowell Discovery Telescope will search for sodium released into the expanding plume.
The Very Large Telescope will search for chemical signatures, including hydroxyl, sodium, and potassium. Professional observatories are not alone. Researchers have also invited experienced amateur astronomers to participate.
Citizen science networks may provide additional recordings from locations that enjoy better weather or viewing geometry.
Even a non-detection matters, because it helps scientists place limits on how dim the impact actually was. This would not be humanity's first artificial impact on the moon, but its circumstances make it unusual.
In 1959, the Soviet Union's Luna 2 became the first human-made object to strike the lunar surface.
During the Apollo era, spent rocket stages were deliberately crashed into the moon at known locations.
Seismometers recorded those impacts, helping scientists investigate the moon's hidden internal structure.
Later missions, including Titan and Smart 1, also ended through controlled impacts on the lunar surface.
In 2009, NASA's LC Ross mission deliberately struck a permanently shadowed crater near the lunar South Pole.
Analysis of that plume revealed water ice, transforming our understanding of resources hidden near the lunar poles.
Later observations indicated that the LCROS impact created a crater approximately 22 meters across.
A separate uncontrolled rocket body impact in 2022 produced an unexpected double crater on the lunar far side.
But the August 5th collision is neither a planned experiment nor a spacecraft following a controlled descent. As lunar exploration accelerates, more machines will travel through the space between Earth and the Moon. Some will eventually fail, become uncontrollable, or remain in difficult orbits that cross future missions. Today, an isolated impact presents little danger. Future astronauts and lunar infrastructure could face a very different situation.
The solution begins with better tracking, knowing what is out there, where it is going, and when it may arrive. As August 5th approaches, telescopes will turn toward a location where the moon may appear completely unchanged.
Perhaps cameras will record a flash. Perhaps they will find a plume. Or perhaps the moon will reveal nothing at all.
Whatever the result, the observations will test our ability to detect and understand a known lunar collision in real time.
Subscribe to Sky Through Time as we follow the events that continue to reshape our view of the universe.
A forgotten machine is approaching an ancient world, and soon, the moon itself may tell us how the journey ends.